In today's lecture, we will pick up what we left off last lecture to first talk about change of basis. After that, we will move on to main topic for today, which is linear maps. So we know the components of a vector are associated with the selected set of basis vectors. In some scenarios, if it is useful to transform the coordinate system. For example, if we are interested in the stress along one direction, but the direction doesn't align with either of the basis sets, then we can change the basis to align with the direction. So here we have an example. So we have this green vector, and the same green vector, because we have different two basis vectors, E1, E2, and E1 prime, E2 prime, and then we will have two different component forms. So it's if we denote this green vector as U in the first basis set, and U prime in the second basis set, then U is equal to 3.2, and U1 is equal to 3.54 and negative 0.72. So they have different components. And now, so how can we describe this kind of transformation? We can link U prime and U using coordinate transformation matrix Q. Now let's think about a general case. If we have a vector in the space, and in the first basis set with the E1, E2, E3, and all the way to En, we can express the vector like this. And in the second basis sets, we have E1 prime, E2 prime, and E3 prime, and all the way to En prime. This vector can be expressed like this. Then its transformation matrix Q will look like this. So now let's take a look at its component form, Qij. Qij is equal to Ei prime, which is the basis set from the second basis set, and Eg, which is from the basis vectors in the first set. And its component form is equal to E1 prime times Eg. For example, the first Q11 is equal to E1 prime times E1, and Q12 is equal to E1 prime times E2, and so on and so forth. Now let's take a look at an example. So in this example, we have two basis sets. The first basis set and the second basis set. The first basis set, we have E1 and E2. E1 is 1, 0, E2 is 0, 1. And in the second basis set, we have E1 prime and E2 prime. And we can express, if we know this angle is theta, so E1 prime can be expressed in the first set, right? So this will be theta. So the first, the E1 prime will have two components, cosine theta and sine theta. And E2 prime is equal to negative, here is a negative sine theta, and here is a cosine theta. Now the transformation matrix is equal to Q11 is the E1 prime times E1. E1 prime times E1, which is cosine theta, and Q12 is E1 prime times E2. So it's sine theta, and Q21 is E2 prime times E1. So it's sorry. So it's lective sine theta, and Q22 is equal to E2 prime times E2. Yeah. So we get cosine theta. Yeah. So yeah, the direction of the theta is counterclockwise, and we think counterclockwise is positive. So transformation matrix has two properties. First, Q times Q transpose is equal to identity matrix. So later on, we will know that Q times Q inverse is also equal to identity matrix. So then we know Q transpose is equal to Q inverse. And second statement is for any vector in Rn space, if we have its component from U1, U2, and all the way to UN in the first basis set, and U1 prime, U2 prime, U3 prime, and all the way to UN prime in the second basis set, then U prime is equal to QU. Any questions? Okay. In this lecture, in today's lecture, we will be focusing on linear maps between vector spaces. So in 2.1, we are always talking about what happens in one space. And now we have added another space. So we are trying to find the relationship between the first space and the second space. These two spaces can be the same. So to start off, let's talk about what is a linear map. Let's take a look at the figure on the right. So a linear map is a relationship between input space and output space. We have two spaces here. For example, if we have in order to visualize, if we have a unit circle here, and after transformation, this unit circle comes ellipse. And this is a transformation. This is a linear map. Later on, we can call it a transformation. So mathematically speaking, we can define it this way. A linear map T between two vector spaces V and W is a function for only two vectors U and V in the input space, and only two scalars, alpha, beta. T has to satisfy additivity and homogeneity. So in additivity, the linear map of U plus V will be the same as the linear map of U plus the linear map of V. And for homogeneity, the linear map of alpha V is equal to alpha times the linear map of V. This is a little bit abstract, so let's take a look at two examples to show us what this all means. So if we have a linear, if we have a map from R to R such that fx is equal to ax, where a is a real number and a is not equal to 0, then we can test if this is a linear map by checking additivity and homogeneity. For additivity, we need to test if fu plus v is equal to fu plus fv. And then we can check the left side first. So fu plus f plus v is equal to a times u plus v is equal to au plus av. And fu plus fv, when we plug in u and v in this, we get au av. So the left side is equal to the right side. Then this map satisfies additivity. Now let's check homogeneity. So we need to check if f alpha v is equal to alpha fv. So for f alpha v, we get we plug in alpha v, we get a times alpha v. And for alpha fv, when we plug in this, we get alpha times a times v. So the left side is equal to the right side. Then we can see fx equals to ax is a linear map. For the second example, we have a function from R to R such that fx is equal to ax plus b, where a and b are real numbers and a and b are not equal to 0. For additivity, we do the same thing. We check fu plus v is equal to a times u plus v plus b is equal to au plus av plus b. And fu plus fv is equal to au times av plus 2b. So the left side is not equal to the right side. So this map doesn't satisfy additivity. Now let's check homogeneity. F alpha v is equal to a times alpha v plus b, and alpha times fv is equal to alpha times av plus b. So it's equal to alpha av plus ab. And the left side is not equal to the right side. Then fx equals to ax plus b is not a linear map. Okay. So yeah, I see a question. So I'm not sure if you can see this. Let me check. And so what value do you get from low-in if a function is a linear map? So linear map is from a space to another space. It's not exact. It's trying to describe a relationship. Here we are trying to map a unit circle to here, but unit circle is just one way to see this space. Actually, it's R2 to R2. So any vector in this space can be transformed to this space. Yeah. So if you still have questions, you can come to me later. Next, we are going to talk about linear maps, the types of linear maps. There are 3 common types of linear maps: injective, subjective, injective, surjective, and bijective. So let's take a look at them one by one. So in a linear map, if each input has a unique output, then we call it injective. Mathematically, it means that for any vectors x and z in the input space, if x is not equal to z, then tx is not equal to tz. In this example, we can see every input in the input space has a unique element in output space. So this is an injective map. Now let's take a look at another example. If we have a function from R to R2. So in order to visualize this, let's assume f11 is equal to 2 and f22 is equal to 1. Then we can see any elements in R2 can be mapped into this line. So 1 will be mapped into this, and 0 will be mapped into 0 in R2 space. However, if we find a random vector here, this one, for this specific vector, you can't track it back because there is no, this vector doesn't has input in from R space. So if each output has at least one input, then we call this linear map surjective. Mathematically, it means for any vector y in output space, there exists a vector in the input space that satisfies Tx is equal to y. For example, we have 5 elements in this input space, and in the output space, we have 2 elements. Each element in the output space has at least one input. So this map is surjective. Now let's take a look at a linear map from R2 to R, and fx is equal to f11 times x1 plus f12 times x2. So in order to visualize this relationship, let f11 equal to 1 and f12 equals to negative 1. So if we have 2 lines in this space, and all the points on this green line will be mapped to this point, and all the points on this orange line will be mapped to this point. So this linear map is surjective because given one output, we can find multiple input. And if a linear map is both injective and surjective, then this linear map is bijective. This means that element in the input space can have one element in the output space, and any element in the output space can have only one element in the input space. For example, the following figure shows a one-to-one correspondence with no element left in the output space. Then we can see that this is a bijective map. A bijective linear map looks like the figure on the right. Notice that when given an input, we can find a corresponding, for example, the black arrow, we can find an output, and with knowing this output, we can track it back. So if a linear map is bijective, then this linear map is invertible. Any questions? Okay. Let's let's take a look at a metric form of a linear map. A linear map can be expressed in a more concise way, matrix. If we have a linear function t from Rn to Rn, so and x is a vector with n components, then we can have the following form of a transformation. Each x can be mapped to a new vector space. For example, if we have a R2 from R2, any point in this space can be mapped to this space, and this space, these two spaces are the same. If we take the input vector x1, x2, and all the way to xn out, we will get its metric representation of linear map. So given this matrix, if we have an input vector, and we can get an output in this space. If a linear map is bijective, then the metric representation of this linear map is a square matrix. So it's n by n. So the input has the n components, and the output also has the n components. Earlier today, we learned that if a vector in space is expressed using two basis sets, then we can use a transformation metric to link them. For example, here we have two vector spaces. It's in the first basis set we have E2 and E1. In the second basis set we have E1 prime and E2 prime. And we can, if we have two vectors here, green one and the blue one, if we express the green one in under the first basis set, we denote it as U. And we denote the green vector as U prime in the second basis set. Then U prime is equal to QU, and Q is the transformation matrix. And now if we add another vector V, and we denote V, we add another vector, is the blue vector. The blue vector is denoted as V in the first basis set here, and V prime in the second basis set. Then can we find a linear map from U to V? The answer is yes. So then we can express V using U. So V is equal to MU. And in the second basis set, we can find the same thing. We can find another metric M prime, which makes V prime is equal to U prime. Now, what's the relationship between M and M prime? So we can just using this formula. We know V prime is equal to M prime times U prime, and V prime is equal to QV, and U prime is equal to QU. Then M prime is equal to QV times QU transpose. So after simplification, it's equal to Q times M times the Q transpose. So here is a little bit confusing. We have two matrix Q. Q is trying to change the basis sets, and M can transform a vector from one position to the other position in the same basis set. So matrix has two functions: change basis and transformation. Now let's take a look at an example. So for this example, we have one blue vector and a red vector, and the blue vector is denoted as U in the first basis set, U1 and E2, and U prime in the second basis of in the second basis set, U1 prime and E2 prime. Then U is equal to Q. Then U prime is equal to QU because we changed the basis. And if we are not going to change the basis and we add another vector, which is V, V is equal to MU. And if we denote if we denote the red vector in the second basis set as V prime, and V prime is equal to M prime times U prime. Given the transformation, we can find and basis transformation matrix, we can find M prime, which is equal to Q times M times Q transpose. Any questions? Now let's talk about determinant. From the previous session, we know that bijective linear maps are invertible and can be represented with a matrix. However, how do we know if a matrix is invertible, especially a higher dimensional matrix? We can use the determinant of a matrix to find out if it is invertible. So if the determinant of the matrix is equal to 0, then the linear map is not invertible. If the determinant of the matrix does not equal to 0, then the linear map is invertible. Now let's take a look at a few examples to calculate the determinant of a 2x2 matrix and a 3x3 matrix. So for 2x2 squared matrix, if a matrix M, which is A1, A2, B1, B2, then the determinant of this matrix is defined as A1 times B2 minus A2 times B1. And the determinant of a two-dimensional matrix also has geometric meanings. For example, if we have this if we have this M2 matrix, and we are trying to transform R2 from any vectors in R2 space to R2 space, and we are trying to transform E1 and E2. So after transformation, we know that M times E1 is equal to A1, B1. See here. So, and after transformation of E2, we have A2, B2. It's here. Then the parallelogram created by X and Y is the determination of this matrix M, and it's equal to A1 times B2 minus A2 times B1. So basically, after transformation, this unit area is stretched like this. Now let's take a look at determinant of the 3 by 3 matrix. If we have a matrix which is A1, A2, A3, B1, B2, B3, and C1, C2, C3, then the determinant of the matrix is the trivial product we learned in our first lecture. And we know trivial product represents the volume. So let's do the same thing. If we are trying to transform the basis sets in the first, we are trying to transform basis vectors in the first basis set, E1, E2, and E3. After transformation, we can get, if we use M times E1, it gives our first column. So it's A1, B1, C1. And we can get our second value, X2 is equal to A2, B2, C2. And L3, X3 is equal to A3, B3, C3. So this volume is equal to determinant of this matrix. So in the input space, we know that the input volume, the volume created by E1, E2, and E3 is equal to 1 times 1 times 1, it's 1. And in the output space, the volume is this determinant of M. So this is simple. And what if we have a hair dimension? So if matrix M is a n by n matrix, then how can we find the determinant of this matrix? We can find the determinant of M using this formula. It's a recursive relationship. The determinant can be obtained by expanding either along the row or along the column. If we expand along the row, then it's equal to every element times the determinant of a new matrix and times the sum and summed them and summed. So this is also a little bit abstract. So let's take a look at an example. Here I'm going to use the 3 by 3 matrix here, which is the A11, A12, A13, A21, A22, A23, A31, and A32, and A33. So if we are going to expand along the first row, then when I is equal to 1, because I is the row number and J is the column number. So when I is equal to 1, the above formula can be simplified like this. So we have 3 elements, A1, A2, and A3 in the first row. And we need to find the new matrix, the determinant of the new matrix and the sign. So the new matrix, by eliminating the row number and the column number of the first element A11 is this. This is the new matrix. And M12 is by eliminating the first row and the second column. So this is our M12. And for M13, we need to eliminate the first row and the third column. So this is our new matrix. And now we need to decide the sign for each component. So for the first one, it's A11. So 1 plus 1 is equal to 2. So it will give us a positive sign. And for the second element, A12, so it's 1 plus 2 is 3. So it's negative. It will give us a negative value. And for A13, 1 plus 3 is equal to 4. So this one is positive sign. So when we sum these 3 components and expand them, it will be this. So this is the triple product, if you remember the expand form of a triple product. Any questions? Okay. Now let's take a look at eigenvalues and eigenvectors. Let M represent a linear map from Rn to Rn, and lambda is a scalar. If we have a vector P, which is not equal to 0, such that MP is equal to lambda P, then we call lambda an eigenvalue, and this P an eigenvector. So what is the geometric meaning of eigenvalues and eigenvectors? If we have, let's see if we have a map from a linear map from R2 to R2. And we can find a vector which is 0, 1 be mapped to the other space, but it didn't change its direction. So this vector is our eigenvector. And all eigenvector is always associated with eigenvalue. It represents the, if we look at this formula, it represents how much we stretch this vector, because it's a scalar. So from the above definition, we know that given a matrix from Rn to Rn, and we are trying to find a non-zero vector P, and a real number such that MP is equal to lambda P. This is equivalent to this. MP minus lambda P is equal to 0, and 0 is a 0 vector. So we need to, after rearrangement, it will become M minus lambda I times the vector P is equal to 0. Now we can focus on how to solve this equation. If we assume this is a new metric like capital A, and A has A11, A12, A13, and all the way to ANN. So we can expand this formula to this. And if we denote A11, A21, AN1 as A1, and A12, A22, AN2 as A2, then we can simplify this into the below equation: A1 times P1 plus A2 times P2 plus A3 times P3, and all the way to AN times Pn equal to 0. This does this look familiar? So this equation holds true only when A1, A2, and A3, and all the way to AN are linearly dependent. So if it's linearly dependent, we can see determinant of A is equal to 0. Then by solving this equation, we can find our eigenvectors and eigenvalues. And M minus lambda I is always called characteristic equations. Let's take a look at a few examples. And for example, we have, for our first example, we have a matrix which is 0, 1, or 1, 0, 0, 1. And we do the same thing. We map a unit circle. We will get a unit circle, which is exactly the same as its original one. So how many eigenvectors do we have for this situation? It's infinite, right? Because the array vectors in the input space is the same as array vectors in the output space. So if we take a look at this matrix, it looks very familiar. If I put it like this, cosine theta, same thing. So this is a rotation matrix. Oh, this is an identity matrix, sorry. So this is an identity matrix. So nothing will change. That's why we have infinite numbers of eigenvectors and eigenvalues. For the second situation, we have a matrix which is 1 1 0 1 1 1 0 1, and if we map a unit circle as what we did before, we can find there is only one eigenvectors, which is 1 0, and this vectors doesn't change its direction, and it was not stretched either because the eigenvalue is 1. So we have if we input this value 1 0, we will get 1 0. Now let's take a look at another example. So for this example, we have 0 4, 0 0.4, 0 0.7, and negative 0.7 and 0.2. We do the same thing. We map a unit circle, and after map, we can't find any vectors that remain its direction. Why? If we take a look at this matrix, we know it's so it's sin theta. It's similar to, it's a rotational matrix. So every vector in the first in the input space will be rotate a degree in the second space. If we take a look at this pink vector, and it will be rotated to here. So for this matrix, there is no real number eigenvectors and eigenvalues. So for next example, we have a matrix which is 1 2 5 1, and we do the same thing. For this matrix, we can find 2 eigenvalues and 2 eigenvectors. So in this graph, we know these 2 directions didn't change after map, and we can see lambda 1 is equal to 4.1623. So along the first eigenvector, it was stretched by 4.1623 times. So we can get the following 2 conclusions. So similar transformation matrix have a similar eigenvalue and eigenvectors. Some matrix may have no real eigenvectors, and some matrix can have an infinite number of real number eigenvectors.